There are moments in science when the universe seems to whisper a secret, barely audible but impossible to ignore. Right now, we might be living through one of those moments. Imagine everything you know about the cosmos, the endless stretch of stars, the dark velvet of space expanding ever faster, the cold equations etched into the backbone of our reality, suddenly cracking at the edges. That's where we are. A quiet revolution is unfolding, not with explosions or collisions, but with a subtle shift in numbers, in light, in time. And at the center of it all is a force so elusive, so haunting, that we named it after what we don't know: dark energy. For over 2 decades, dark energy has been the invisible hand accelerating the expansion of our universe. It came into the picture in the late 1990s when astronomers noticed something deeply counterintuitive. Instead of slowing down, the universe was speeding up, as if being pushed apart by something unseen. It was a revelation that shattered our expectations. To account for this, scientists inserted a new term into Einstein's equations: a cosmological constant, something steady and unchanging. This became the cornerstone of what we now call the Lambda CDM model, the standard map of how our universe grows. But now, with chilling precision, something in that map is starting to look wrong. At the heart of this unraveling story is a machine. It stands high on Kitt Peak in Arizona, nestled beneath a dome that opens each night to the heavens. Inside, 5,000 robotic fibers reach for galaxies like mechanical arms plucking threads from the cosmic tapestry. This is the Dark Energy Spectroscopic Instrument, or DESI. It doesn't look dramatic, but what it's doing might be one of the most important missions in modern science. DESI is reading the history of the universe in the light of galaxies billions of years away. Light that's traveled through an expanding cosmos, warped and stretched like time itself. Each pinpoint of starlight carries a story. It tells us how far that galaxy is, how fast it's moving, and when it emitted that light. But more importantly, embedded in these streams of ancient light are patterns, ripples frozen from a time when the universe was still a dense, glowing plasma. These ripples, called baryon acoustic oscillations, act like a cosmic ruler. They show us how the universe has grown, inch by inch, epoch by epoch. When DESI released its first wave of data, scientists noticed something odd. The numbers hinted that dark energy, this force we've long believed to be constant, might actually be changing. At first, it seemed like a fluke. Data can be messy. Patterns sometimes emerge where none exist. But science is patient. It waits. And DESI kept watching. Then came the second wave. With even more data, the pattern didn't go away. It became clearer, stronger, almost undeniable. What was once a whisper now had the weight of a near discovery, hovering at about 4.8 sigma, just shy of the gold standard of 5. In plain terms, this means the signal is strong enough to take seriously. It's not conclusive, but it's no longer safe to ignore. The implications? They're enormous. If dark energy is changing, even slightly, then our entire understanding of the universe must shift. The idea that dark energy is a constant may be wrong. The force that is stretching the fabric of space could be weakening, and that changes everything. To verify this, scientists didn't just rely on DESI's findings alone. They turned to other cosmic markers, type Ia supernovae, which act as reliable distance candles across the cosmos, and the cosmic microwave background, the faint afterglow of the Big Bang. Each of these is like a checkpoint in time. By combining these threads, supernovae, BAOs, and the CMB, they wove together a far richer picture of the universe's expansion than any one method could provide. And the new picture doesn't quite match the old map. When the DESI data is layered over this multi-tiered structure, the cracks in the Lambda CDM model become even more pronounced. The universe doesn't behave the way it's supposed to. It's not just that dark energy might be changing, it's that a model where dark energy does change actually fits the observations better. It's a better match for reality. That's a seismic shift. But here's the thing. Science doesn't leap until it has to. And right now, the field is holding its breath. Is this just a momentary anomaly? A statistical fluke? Or is it the first glimpse of something bigger, something deeper? The model where dark energy weakens is compelling, but it's also, in a sense, ad hoc. It fits the data, yes, but there's no grand theory underpinning it, no elegant framework explaining why dark energy would behave this way. It's like being told the ocean tides are suddenly doing something strange, but no one knows why the moon would be behaving differently. That sense of mystery, it's electric and terrifying. If the data holds, we may be forced to admit that dark energy is not some passive, silent backdrop. It's active, evolving, maybe even alive in some abstract way. The universe is not just expanding, it's reacting. And that reaction might hint at a cosmic destiny different from anything we imagined. This is where we stand, not at a conclusion, but on the edge of a new beginning. We are staring at a puzzle that refuses to stay solved. And in the next few years, with more data and sharper instruments, we might finally begin to understand what the universe is trying to tell us. As the whispers of a changing universe grow louder, the world's top cosmologists are caught between wonder and disbelief. After all, the idea that dark energy might be shifting isn't just a minor tweak. It's a thunderclap against the very structure of modern cosmology. For decades, the Lambda CDM model has stood like a lighthouse, guiding physicists and astronomers through the unknown. It's been tested, refined, confirmed again and again through observations of everything from galactic clusters to the faint echo of the Big Bang. But now, that beacon seems to be flickering. What DESI and its collaborators have uncovered is subtle but relentless. The expansion history of our universe isn't following the neat trajectory we once believed. It's like noticing that a clock you've trusted for years has begun to tick just a little offbeat. At first, you might ignore it. But if the ticking keeps drifting, you can't deny it forever. That's where we are. The measurements suggest that dark energy may not be constant, that it might, in fact, be getting weaker. If so, that means the force accelerating the cosmos is slowly winding down. To understand why this matters, consider the role dark energy plays. It's not just some esoteric term buried in equations. It's the reason galaxies are racing away from each other faster and faster. It's why the night sky will one day grow colder, dimmer, lonelier. If dark energy fades, that future changes. The expansion could slow, it could stop. In some distant age, it might even reverse. Galaxies could begin to drift back together. The universe could collapse, not with a bang, but with a cosmic sigh. And yet, for now, the numbers are still not quite definitive. Science demands rigor. A 5 sigma detection is the threshold, 5 standard deviations from randomness, the statistical holy grail. At 4.8 sigma, we're standing at the door, hand on the knob, but not quite ready to turn it. That's why scientists are being cautious, and rightly so. But the momentum is building. To tighten the picture, researchers are weaving together different strands of the cosmic story. One thread comes from type Ia supernovae, massive stellar explosions that shine with such consistency that they can be used to measure vast cosmic distances. They're like streetlights on the highway of the universe, marking how far we've traveled and how fast we're going. Another thread comes from the cosmic microwave background, or CMB, the afterglow of the Big Bang itself. It's the oldest light we can see, a snapshot of the infant universe frozen in time. The CMB tells us how the universe began, while supernovae tell us where it's going. When you link these extremes with DESI's midpoint measurements of galactic expansion using baryon acoustic oscillations, you get something beautiful. A timeline stretching from the dawn of time to today. And it's that full timeline, The marriage of rulers and candles, of ancient echoes and fiery deaths, that's revealing the tension. The Lambda CDM model predicted one thing. The real universe, it seems, is doing something else. Of course, not everyone is ready to abandon the old model. Some argue that the data could still be skewed by subtle errors. Measuring the cosmos is not easy. Every step, every calibration of a telescope lens, every brightness reading of a distant supernova comes with uncertainty. The deeper we peer into space, the more fragile our assumptions become. Even the standard candles we rely on can flicker, mislead, or change subtly depending on the environment around them. But despite these challenges, confidence is growing. Scientists are refining how they analyze light, recalibrating their instruments, and preparing for an even more detailed view of the cosmos. New missions are in the works, promising sharper, cleaner data. Future telescopes, both ground-based and orbiting, will look deeper and farther than ever before, chasing the evolution of dark energy across space and time. It's worth asking, if dark energy really is dynamic, what is it? That question cuts to the heart of the mystery. For years, dark energy has been modeled as a kind of vacuum energy, predicted by quantum field theory. But if it's changing, that theory might be incomplete or wrong. Maybe dark energy is more like a field, something that interacts with space itself. Maybe it's tied to new, undiscovered particles or forces. Some even speculate it could be a sign of higher dimensions bleeding into our universe, or the fingerprint of a deeper multiversal structure beyond our reach. These are wild ideas, but the data is forcing us to consider them. In the face of such possibilities, scientists are doing what they've always done in moments of uncertainty. They're doubling down on observation. They know that the answers lie not in guesswork or theory alone, but in light. Ancient light, bent and red-shifted by billions of years, carrying messages from across time. The DESI instrument, with its 5,000 robotic eyes, is just the beginning. Future surveys will push even farther. The Vera C. Rubin Observatory will scan the sky with breathtaking speed and depth. The Euclid mission and the Nancy Grace Roman Space Telescope will chart the geometry of the universe with unparalleled precision. Each new data set will be another piece of the puzzle, another chance to see if this strange shift in dark energy is real or just a statistical ghost. In the meantime, there's a sense of something momentous hanging in the air. It's the feeling of standing at the edge of a forest you thought you knew, only to hear the trees whispering something different. The models we built were good. They guided us for decades. But now the forest seems deeper, darker, and more alive than we imagined. And the universe, once thought to be calmly drifting outward forever, may be stirring with something far more dramatic. Here we are, staring into a universe that might not be expanding the way we thought. For decades, we believed dark energy was this smooth, unchanging push, something built into the fabric of space-time itself. But now, the numbers are whispering a different story. What if that mysterious force is evolving? What if the cosmos isn't locked into a forever accelerating future, but is instead on a shifting path, one we've only just begun to glimpse? The DESI team's results aren't just data points. They're signposts on a winding road, suggesting that our understanding of the universe is too simple. With every new observation, it becomes more likely that dark energy isn't constant, and that means our deepest cosmological framework might need rewriting. A weakening dark energy could slow the expansion, maybe even stop it. It might be a clue that dark energy is tied to something bigger, deeper, stranger. Something we haven't yet discovered. And that realization changes everything. It forces us to ask terrifying, wonderful questions. Are we watching the end of cosmic acceleration? Is the universe drifting toward balance or collapse? Could this lead to new physics, new dimensions, new insights into the very code of reality? Scientists aren't jumping to conclusions, but they're looking harder than ever. With better data, sharper instruments, and a renewed urgency, the search is on. Because if dark energy isn't what we thought, if it's not constant, not simple, not solved, then we've been living inside a mystery all along. And now, finally, we might be close enough to see what's behind the curtain.